Hello, my name is Samuel Trent, and for my ECE 570 project, I performed an analysis of the number of shots in few-shot text classification learning. The motivation for this idea was to be able to take text data straight from the web and classify it into categories that a user finds interesting, essentially creating a For You page for all sorts of different types of data such as news, research, and tweets. The first paper that I implemented was from ICLR, Few-Shot Text Classification with Distributional Signatures. This algorithm attempted to apply few-shot meta-learning, a concept that was popular for low-resource computer vision, to text classification. This few-shot method works well with images because low-level input patterns are transferable across learning tasks. However, it is much more difficult to apply to text scenarios because words highly informative to one context may not be important at all to another. This paper overcame this challenge by using two separate steps, an attention generator function and a ridge regressor. The attention generator creates an informative attention score that is used by the ridge regressor to construct a model to classify query input. Here's a block diagram of the execution. In block A, the attention getter downplays the importance of frequently occurring words and calculates word importance to the context. Because these two statistics are noisy and contain complementary information, they are combined with a bidirectional LSTM function to fuse the final attention score as a function phi. Phi is passed to the ridge regressor and applied to the testing and training set to calculate the final prediction. I ran into major problems when trying to implement this method. After getting the code installed and running, it crashed my computer and it was finally able to execute. After talking to Professor Anoye in office hours, he suggested finding a different algorithm to implement that didn't take 18 days to fully execute, or finding ways to adjust the parameters of this algorithm to find similar results. I explore both of these options in the following slides. First, I found a much simpler algorithm in a JMLR article. It's a weka package called Effective Tweets, which provides many data pre-processing functions and a fast and efficient linear regression model. And the biggest plus of this was that it ran smoothly on my computer. Next, I found another ICL article which performed a theoretical analysis of the number of shots in few-shot learning. Its research focused on two main features of the algorithm, primarily the number of shots, or examples of correct input to the algorithm, and the number of dimensions to the input. From this paper, I theorized that using scarce amounts of training data while increasing the number of shots would improve my original algorithm's performance. Additionally, I wished to test the hypothesis that increasing the dimensions of input to a training algorithm will eventually degrade the accuracy of that algorithm. I tested these two theories with the two algorithms that I previously discussed, and I will share my results in the following slides. Because execution through the training stages was the biggest limiting factor to my first algorithm's implementation, I wanted to reduce the number of training episodes in order to get the code to run to completion. But this cost me a lot in accuracy. From the analysis article, I hypothesized that if training were made scarce and the number of shots were increased, that I would be able to achieve similar performance that the article found. So I cut the training data by a factor of 4, increased my number of shots, and was ultimately able to reduce the runtime of my code from 18 days down to 6 minutes. With the shots held constant at 1, my algorithm performed significantly worse than the paper's algorithm, with mine achieving 69% accuracy compared to the paper's 81%. However, as the shots were increased, I was able to show that my algorithm exceeded the performance of the paper, all the way up to the paper recorded results with a maximum of 5 shots, and it took my algorithm 15 shots to achieve their same 5, but I was still able to achieve the same results. My second evaluation was on the pre-processing of input data. From the analysis research paper, I hypothesized that increasing the number of dimensions to the input would have upper bounded results on the accuracy of the algorithm. Throughout each test, I performed additional pre-processing of input data and tested the input data using a fast linear classification algorithm. Starting with just one input dimension, I had low accuracy, as expected, but as dimensions were added, I was able to achieve a maximum accuracy of 78.8%. Then the model became more susceptible to overfitting, and the accuracy began decreasing with each additional features being added. So my final take-home messages are that complex few-shot algorithms can be adapted to low processing power environments by stripping input dimensions while parallelly increasing the number of shots used by the algorithm. Additionally, it is important to consider the amount of pre-processing dimensions you add to an input dataset before training an algorithm, and more is not always better.